Alrighty, so let's look at questions 11 through 15. 11 says, how can you use a graph to make sure that the inverse of said graph is a function? Okay, so we're saying, how can we use this graph to make sure that its inverse is going to be a function? So let's say that we have this graph right here. And if I take the inverse, I'm essentially reflecting it across this line y equals x, just like we did in class in the notes. So that means, for instance, if I did this by hand, because I want to make sure that you understand how to do this by hand, I could pick points like 0, 0, which will go to 0, 0. Or I can pick points like, let's say this is 1, and this up here is 5. Okay? It's like an approximation. So 1, 5 would change and flip, because inverses, the x and y flip, to 5, 1. So 1, 2, 3, 4, 5, and then 1. Okay? That's where this point is going to go. And all I did was flip the x and the y. Let's pretend this over here is like 1, 2, and then up by, like, say, 10. So this is like negative 2, 10. Well, then to flip it, you'd go 6, 7, 8, 9, 10, and a negative 2. And it would be way over here. And if you were to do a rough sketch, and that's why I'm doing it this way, it's just a rough sketch, basically it would reflect, that looks something like this. And yes, if you imagine this as y is equal to x and you folded it like a piece of paper, it does look like this piece here would end up reflecting to become this, and this piece of the original graph would reflect and become this. And the thing is, how can you make sure that this is going to be a function? Well, it has to pass the vertical line test. So, you draw the inverse, and then the inverse must also pass the vertical line test. Now, this one obviously doesn't, and we're going to talk about this very soon as far as how you can quickly identify this. And this is how I'll explain it to you. The original graph was this one right here in gray. And we know that its inverse will not pass the vertical line test if, on the original graph, it doesn't pass the horizontal line test. So a horizontal line test is used just the same as an inverse in the fact of you're trying to see, are there multiple values that are going to hit this graph? Okay? So you see right here and right here, it's gonna hit the graph twice. So it's gonna fail the horizontal line test. And if it fails the horizontal line test, that means the inverse will fail or not pass the vertical line test. Okay? So the inverse must also pass the vertical line test. In this particular instance, we know that it will not. Okay? But sometimes you will have graphs that, let's say that you have this graph right here, just that piece, and if you reflect it across y is equal to x, it would become just this piece. And yes, the original one did pass the vertical line test, and the inverse also passes the vertical line test. So sometimes you will have it, you just have to check. Okay, let's go to number 12. It says, sketch the graph of the inverse in this relation. Okay, so I'm going to pick some points. This one right here is negative 4, 0. So the inverse is going to be 0, negative 4. All I did was flip the x and the y's. Let's pick a point on the original graph. Another one. Let's say we picked 0, 4. And where this will end up being on the inverse is, again, flip the x and y, will be at 4, 0. And last but not least, let's pick another point on the original graph. Let's say that I picked this one way down here, which was 0, negative 4. So that's going to flip and become negative 4, 0. Now I know this looks a little bit weird with this last point going on. So if you're a little confused with this last point, you can pick a different point still on the original function. Okay? Let's say that we picked negative 2, 2. It's kind of almost there. Negative 2, 2. Well, then the one on its inverse would be at 2, negative 2. Okay? So you're just going to flip them and have 2, -2. Okay? So you have this piece right here for sure is one of them. And you're probably thinking, how about the piece here? How about we pick a point from there? So let's say on the original, I picked a -2, -2. Well, on the inverse, it's also going to be -2, -2. Because if you flip the x and y, you still get that same point. So the graph looks like that. So the inverse would be this graph right here. All right. So number 13, it says use interval notation to represent the set of numbers of x's between -7 and 3. Okay? So let's move this up just a little bit. So if we're going to use interval notation, we're thinking about parentheses or brackets, one of the two. So if I'm going from -7 all the way to 3, and it's basically looking at visually like at -7, it's going to be closed. At 3, it's going to be closed or filled in. And then it's everything in between. And if I'm doing this interval notation wise, I'm going to say from -7 all the way to 3, and both of them are going to be closed because of that equal sign up here. Remember, if it's just greater than or less than, you're going to have parentheses. If it's greater than or equal to, or less than or equal to, or greater than or equal to, you're going to have brackets. So there's your pieces. All right, so let's move on to number 7. Or sorry, 7. 14. 14 says just simplify this expression, combine all like terms. So I have x squared, I have another x squared, which means I have 1 and 5, which add up to give me 6x squared. There are no other like terms, so we're just going to write them out in descending order. All the s squareds first, all the s to the power of 1's next, and then we can put the t on the very end. And that would be the simplified form. So combining like terms. And finally, number 15. It says give the domain and the range. Remember, this has to be on the test for you not to lose points, the notations of D and R. And we're going to say of the relation. So right now, this graph, if I were to draw this like points, I have 2, 5. I have 8, 17, which is way here and way up here. Then I have 0, 0, and then -3 and -5. These points, because it's a relation, are not going to be connected. Like if it was wanting to be connected and it wanted us to show those pieces connected, we would have seen piecewise functions. Okay? And there would have been 3 pieces, the functions themselves, and then the domains. Where were they defined? Okay? But that's not what we have here. We just have a relation. So by default, relations can just be seen as points. So discrete, non-connected, all separated points. Okay? That's the default that we're interpreting a relation with. So we have just these points. So if I'm going to list the domain, all I'm going to do is list the x values. And it's kosher to list them in least to greatest order. So you'll have these set notation braces that are showing that these are individual elements of the domain. Okay, so there's nothing is connecting. Everything is its own little island, if you will. And the same with range. We're going to have this set notation from least to greatest as far as the y values are concerned. Now notice, I don't have these braces with something like x such that. So I don't have a domain where x, a set of all x's such that, and then we have pieces after that. I want to make sure that you understand the difference. These such that moments, they're for intervals. Something like up here that we saw in question number 13, where you could see x's that exist between. Remember that we were combining algebraic notation and set notation together, but nonetheless we were given this as far as an interval in some sense. They weren't just discrete points that were sitting all by themselves. They were connected points in some way, shape, or form that said we would use this notation with this x such that specific notation. If you don't see those connections and they're all just discrete points, almost like islands all by themselves, you're going to use this notation right here. All right.